let us discuss now synchronous counters. In the case of the ripple counters, we were able to use the flip-flops which were directly having the T flip-flop operation. Such flip-flops we were able to use directly in the case of the ripple counters. And in the case of the ripple counter, if you want to have a switching sequence for the counter something like this, a switching sequence something like this, if you want to have such counter design is not possible in the case of ripple counters. But whereas coming to the synchronous counter, we are having a possibility to use any sort of flip-flop. There is no bar on any flip-flop. If you want, we can use any flip-flop. A part of the standard flip-flops, while discussing the flip-flop conversions, we were talking about some AB flip-flop. Even such AB flip-flop also we are having possibility to use in the case of this synchronous counters. And also in the case of the synchronous counters, we are having a possibility to design the counter even such random sequence something like this. We'll be having more flexible work with the synchronous counters. For a user point of view, they are more flexible than ripple counters. Let's try now here a 3-bit synchronous counter. We are looking here in this circuit. We are using 3 flip-flops. All the flip-flop clear terminals are connected to the common terminal. All the flip-flop preset terminals also connected to the common terminal. And we already mentioned the meaning of synchronous and asynchronous. Based on this, we can able to see all the flip-flops. Of course, we consider the flip-flops are the positive triggered flip-flops. All these flip-flop clock is common from the external source. We want to have initially all these flip-flop outputs to be 0. So we want to read initially all these flip-flop outputs to be 0. That is Q2, Q1, Q0 we want to read as 0. So to read all the flip-flop outputs to be 0, we need to apply clear 0 preset 1. While applying the clear 0 preset 1, we'll be reading all the flip-flop outputs to be 0. Later we want to apply the clock signal. To apply the clock signal, clear and preset both must be connected to 1. While connecting clear and preset both to 1, while applying the clock signal, we want to have a switching sequence in this circuit like this. After first clock pulse, we want to have the state of the counter is to be 001. After second clock pulse, the state of the counter must be 010. After third clock pulse, it must be 011. After fourth clock pulse, it must be 100. After fifth clock pulse, it must be 101. After sixth clock pulse, 110. After seventh clock pulse, it is 111. After eighth clock pulse, it must back to 0. It is a switching sequence what we want to have in this counter. As and when we are looking, external clock is common to all these flip-flops. Then, based on the switching sequence we look, suppose consider present state of the circuit is 101. After applying the clock signal, we want to have the Q0 must change 1 to 0. Q1 must change 0 to 1. And Q2 must change 1 to 1. So that while having it is present state as 101, we are looking to the next state of the counter is 110. Similarly, if at all it is the present state of the counter, while applying the clock signal, we want to have the counter must get the state as 101. It means Q0 must change 0 to 1, Q1 must be remain same 0 to 0, Q2 also remain same 1 to 1. If at all we are looking like this, if you name any state as the present state, the next state we are looking always just below the present state. So that we are looking on each and every flip-flop from this table. If at all we are looking from this table, we are able to see on each and every flip-flop we know what is the present state and what is the next state after applying the clock signal. So we are able to look from this table description on each and every flip-flop, what is the present state and what is the expected next state after applying the clock signal.